The question says at any time t, when question number 1, this is in practice paper 23. At time t equal to 0, the activity of a radioactive substance is 1600 BQ. BQ stands for becquerel. Becquerel is the unit for radioactivity. And at t equal to 8 seconds, the activity falls to 100 BQ, which is becquerel. Okay. At the activity at t equal to 2 seconds, you have to figure out. Okay. Let me repeat the question. At any time t equal to 0, the activity of a radioactive substance is 1600 becquerel. At time t equals to 8 seconds, the activity falls to 100 becquerel. What will be the activity at time t equal to 2 seconds? Okay. So first thing, always remember the activity. Okay. Let me write activity for any radioactive substance at any time t is equals to R naught, okay, into half to the power t, and this t divided by the half-life of that substance, t half. Okay. What is half-life? I have already explained in the previous lecture also. And t, the time. R is your activity, okay, or rate you can say. So rate of your decay is called activity of radioactive substance. So R equals to R naught, half to the power t by t half. Clear? Now if here given as, if R naught, which is initial, okay, activity, that is 1600 becquerel. R naught is 1600 becquerel. And what is R? It is falling to the final state. R is equals to 100 becquerel. Okay. What is the time? Time is our 8 seconds. In 8 seconds, it is going from 1600 to 100. So time is 8 seconds. Okay. First, we will have to calculate the t half of this particular nuclei. T half is half-life of this particular nuclei. So let's substitute here. So R is how much? 100. That is equals to R naught 1600 half to the power t, which is 8 upon t half. Let's take here 1600 on the left hand side. It will become how much? 1 by 16. That is equals to half whole power 8 upon t half. This 1 by 16 can be written as 1 by 2 whole power how much? 4. That is equals to half whole power how much? 8 upon t half. Now half both the sides, so powers must be equal. So here we can write 4 equals to 8 upon t half. Now t half from here we got it as 2 seconds, which means after t equal to 2 seconds, the nuclei which are remaining, they will be 50% of the original number of nuclei. And what was the original? 1600. So after t equal to 2 seconds, it will be 50%, which is 800. So correct answer for this first question is option B. Let's move to the second question. Okay, great. This is our second question on the screen. Question number 2 says, if the kinetic energy of the particle is increased to 16 times its original value or the previous value, the percentage change in the de Broglie wavelength we have to figure out. Let me repeat again. If 16 times you are changing the kinetic energy, what will be the change in the de Broglie wavelength of the given particle? Clear? So this is direct question, very simple from dual nature chapter. We know that the wavelength is lambda equal to h upon p, where p is what? Momentum. And how do we convert momentum into kinetic energy? Lambda will be equals to h upon p. P is how much? Root under 2 times m into kinetic energy k. I hope this is clear. Now here the kinetic energy, this is your lambda, okay, your relation between wavelength and the kinetic energy. Now what is happening? The kinetic energy is changing to 16 times its original value. So let's call it as lambda dash, okay, lambda prime, that is equals to h upon root under 2m into k will be what? 16 times its original value, 16k. Clear? Now let's simplify it. It will be equals to h upon 16. When you take it out root, it will be how much? 4 times root under 2mk. Correct? Now h upon 2mk, that is nothing but what? Lambda from the green equation. So lambda by 4. Clear? So the new wavelength, when the kinetic energy becomes 16 times original kinetic energy, the wavelength becomes 1/4 of its original wavelength. Clear? So lambda prime is lambda by 4. And how do we find percentage change? From very basic 10th standard. Percentage change is the new one minus the old one, okay, or the old one minus the new one, whatever, okay, magnitude it is. Let me put a magnitude, whole divided by the old one into 100. Correct? This is the percentage change, right? Okay, for example, I had 2 chocolates and it became 8. So what is the percentage change? 8 minus 2 divided by 2. 2 were the original. So lambda prime here is small. So let me just find the magnitude. Lambda by 4 minus lambda whole divided by lambda into 100. And that will be, I am ignoring the negative sign because it's modulus. So 3 by 4, okay, 4 minus 1, 3, 3 by 4, lambda cancels into 100. And 3 by 4 of 100 is 75%. Okay, that's 75%. Because 4 25s are and 25 3s are 75%. So what is the change in the de Broglie wavelength? 75% it will change its original value. Let's move to the next one. Question number 3 over here. Great. So question number 3 on the screen. It says if nu1 is the frequency of the series limit of Lyman series. Okay, nu1 is the frequency of any Lyman series. Nu2 is the frequency of the first line of Lyman series. Okay, there are different lines. So the limit is nu1 and nu2 is the first frequency of the first Lyman series. I hope all of you are familiar with Lyman, Paschen, okay, all these, Balmer, all these series. Okay, so first line of Lyman series, and nu3 is the frequency of the series limit of Balmer series. Then what is the relation between each one of them? Clear? So let me now recall your basic concepts of Lyman, Balmer and all. Okay, so what happens basically if an electron is jumping from any higher energy level, to the energy level 1, E1, then the series we call it as Lyman series, and the frequency of that is equals to RC into 1 upon 1 square minus 1 by n square. Let's not make it, okay, let's make it n square. N is the any higher energy level. Now some of you will say, sir, we have learned this relation in terms of wavelength. Okay, so you can take this C on the left hand side and nu by C, you can make it 1 by lambda, and that will be the same thing, right? Okay, so in case if you have learnt it like this, 1 by lambda equals to R, okay, into 1 by 1 square minus 1 by n square. This is Lyman series. Fine, it's the same thing. Lambda is, okay, you can make it as C by nu and you can take it on the other side, this C, and you will get. So both are the same relation. Okay, this is Lyman. When here it is 1, it's Lyman. When here it is 2, it's Balmer series. When here it is 3, it's Paschen, and so on. Clear? So this is your Lyman series formula written in green. Okay, and for series limit, what is the limit? Limit means the last one. Last one. So for series limit, n will, I am writing here for series limit. What's the frequency? Frequency is nu1, and what will be the value of n here? Value of n will be infinity. Infinity means infinity square is infinity, so I am just keeping it as infinity only. So 1 by 1 square 1 and 1 by infinity 0. So nu1 will be equals to RC. This is your equation 1. What is nu1? The series limit. Series limit means the last spectral line which you can observe. Clear? Now what will be the first one? Sir, for first one, see, if an electron is jumping to the first energy level, okay, n has to be 2, right? It can jump from second floor to first floor, okay? You can't jump from first floor to first floor, okay? Provided if you are taking, sir, I am sitting on a table on the first floor and then I am jumping on the first floor, then that is first floor. But in these situations, when electrons are jumping, you can't have a table or chair on the first floor, okay? So if an electron is jumping from the second will be the first spectral line, right? So for first spectral line, here you have how much? nu2 is the frequency, and RC, this will be 1 upon 1 square minus 1 upon 2 square. I hope this is clear why I made it 2. 2 because it is jumping from second to, okay, and second to first means that's a first spectral line you can see. Let's simplify and check what we get. So 1 by 2 square, 1 by 4, and 1 minus 1 by 4, that is 3 by 4. So this will be simply 3 by 4 RC, equation number 2. And what about nu 3? Nu 3 is the frequency of series limit for Balmer series. So what's our Balmer series formula? Just now we said nu equals to RC 1 by 2 square. When any electron is jumping from higher energy level to the second level, it is Balmer series minus 1 by n square. Now for series limit, n will be infinity, right? So this will be simply 0 second part, and 1 by 2 square is 4. So RC by 4. This is our equation 3. Now they are saying what will be the relation between each one of them, which one is true. So nu 1 is this RC, nu 2 is 3 by 4 RC, and nu 3 is RC by 4. Okay, let's try to figure out a relation. So if we add this one, let's put it in first equation and check. Nu 1 is how much? RC. So let's put here RC. I'm putting in the first equation. Okay, if this is not holding true, then I'll put it in B, C and D. RC minus nu 2 is 3 by 4 RC and equals to nu 3. Let's check. So on the right hand side it's RC by 4. Okay, so let's solve the left hand side. So 4 RC minus 3 RC by 4. Yes, first one is satisfying. So correct answer is option A. Nu 1 minus nu 2 equals to nu 3. Okay, that's our correct answer for question number 3 in practice paper 23. Okay, great. Let's move to question number 4. Question number 4 on the screen. A reactor is developing energy at the rate of 3000 kilowatt. That's the energy, 3000 kilowatt. Clear? How many atoms of uranium-235? I hope all of you have heard of this type of fissionable materials. Uranium, okay, 235 and 238, they are fissionable materials which can undergo fission, nuclear fission. What's nuclear fission? Splitting of a heavy nuclei into smaller nuclei. That's called as nuclear fission. And sir, why do they want to split into lighter nuclei? Because the number of neutrons inside the nuclei keep on increasing as you go along the periodic table when you have higher elements, and these neutrons will make instability inside the nuclei. Nuclei becomes bulky, so they will try to split into lighter nuclei. Okay, that we also call as daughter nuclei. What are daughter nuclei? When any heavy nuclei, a parent nuclei like uranium-235 or 238, when it undergoes fission reaction, the lighter nuclei which is produced are called as daughter nuclei. Okay, let's read the question once again. It says a reactor is developing energy at the rate of 3000 kilowatt. How many atoms of uranium-235 undergo fission per second if 200 mega electron volt energy is released per fission? Beautiful question. Let's see. So first of all, what is the rate of developing energy? 3000 kilowatt. Let's multiply this kilowatt into 10 to the power 3. That will be watt. And what is watt? Sir, watt is joules per second. So we can write it as 3 into 10 to the power 6 joules per second. Great. And what is that? Okay, this is our equation 1. This is what? Rate of developing energy. Okay. So let me write here energy. Rate of developing energy is this much. Next is, what is the energy released in fission energy? So fission energy is energy released in fission. That is 200 mega electron volt. Now some of you, those who are confused with mega and million, it's same thing. 200 million electron volts. So million will be 200 into 10 to the power 6. And to convert this electron volt into joules, I'll have to make it multiply with 1.6 into 10 raised to minus 19. That will be converted into joules. Great. The question says how many number of atoms which are undergoing fission per second. Okay, so this is the energy developed in the nuclear core. This is the energy released by the fission reaction. So how many are going under this? Let's see. So that you have to basically find the frequency, okay, of atoms. So frequency means you can see here it is joules per second and it is joules. Okay, you can divide both to get the value of number of atoms. So number of atoms undergoing fissions will be equal to the energy which is developed in the core and the energy upon the energy given by the fission. So 200 into, let me just make it simplified, these two zeros and here 6, 8 and 10 to the power minus 19 and 19 minus 8, 11 and 16 to the 32, so 3.2. I hope this is clear. Let's take this 10 to the power, okay, let's make it as 32 and make it 10 to the power minus 12. Okay, so this will be 3 upon 32 and 10 to the power 12 goes on the top, it will be 10 to the power 12 and 6, this will be 18. So this can be written as, let me directly divide it, and that will be 0.093. So 9.4, let's round it off, 9.4 and into 10 to the power 16 because it's 0.09. So that's option B here. Direct and simple question. Let's move to our question number 5. So question number 5 is over here. Yes. Okay. So question number 5, it says the wavelength of the first line of a Lyman series of hydrogen atom is equal to the second line of Balmer series of the hydrogen-like ion. The atomic number Z of hydrogen-like ion is how much? Okay. Very simple and direct question. Let me repeat again. Okay. The question says the wavelength of the first line of Lyman series. Just now we did one problem on Lyman series. What's a Lyman series? Our nu was equals to RC into 1 by 1 square minus 1 by n square. This is in terms of frequency. Now if I take the C on the other side, the same formula I have given you, 1 by lambda, because they are talking here in terms of wavelength. So 1 by lambda equals to R into 1 by 1 square minus 1 by n square. Similarly, in case of Balmer series, this 1 will be replaced by 2 square, right? Let's read the question now. The wavelength of the first line of Lyman series. First line I have already explained you. It will jump from second level to first level. So first line will be, I am writing here first line, that will be 1 by lambda equals to R into 1 by 1 square minus 1 by 2 square. I hope this is clear. Okay. Now they are saying this is equation 1. Okay. This is equal to the second line of the Balmer series. Okay. So, and Balmer series, and that too of a hydrogen-like ion, not for hydrogen. If it is for hydrogen, then we use this formula. If it is hydrogen-like ion, okay, then for that the same formula will be, this is for second line of Balmer series. Pay attention, second line Balmer series. 1 by lambda equals to Z square, I am writing here lambda prime, Z square R 1 by 2 square, and second line will be, so after, see, if it is 2, so who can jump from higher energy level to 2? The first one will be 3, correct? You can have, if this is second floor to second floor, you can jump from third floor, that will be the first, and the second will be fourth floor. So you can jump from fourth floor to second floor. So which is the second line for Balmer series? 4 to 2. Which is the first line for Balmer series? 3 to 2. Which is the third line for Balmer series? 5 to 2. I hope this is clear. Okay. So let's substitute here. So it will be 1 by 2 square minus 1 by 4 square. That's our second line. Sir, why you wrote here Z? Z is actually there for all the series, for Lyman, Balmer and all. But since we are dealing with hydrogen atom, this Z value becomes 1. Atomic number is 1 for hydrogen atom. So we are mostly asked with hydrogen atom. Here they are asking hydrogen like. Sir, can you give an example of hydrogen like atom? Helium, if you take helium, which contains 2 electrons, 2 protons and 4 is the mass number. Now in the outermost shell of the helium atom, there are how many electrons? 1s2. I hope all of you are familiar with electronic configuration, 1s2. So out of that 1s2, if you remove 1 electron, how much you left with? 1s1. And that's the electronic configuration of hydrogen atom. So is it hydrogen atom? No, it's hydrogen like ion. Similarly, if you remove 2 electrons from lithium atom, you will get again hydrogen like ion. Clear? So in case of hydrogen, we don't take this Z formula in our Lyman and Balmer series, this formula, because their Z is already 1, so no need of specifying. Here we are specifying because it's a hydrogen like. Now they are saying they both are equal, right? Let me read the question once again. The wavelength of the first line of Lyman series for hydrogen atom, which is the red equation, is equal to the second line of Balmer series for the hydrogen like ion. So that is equal to the second equation. Let's equate both. So when we equate both, okay, what will happen? You will have the left hand side will be equal to left hand side and right hand side will be equal to right hand side. So let's equate right hand side only because we want Z and not lambda prime. Okay. So this will be 1 r upon 1 upon 1, 1 and minus 1 by 4, and that is equals to Z square r, and this will be 1 by 4 minus 1 by 16. So r and r cancels out, and let's see what we get. 4 minus 1, 4 minus 1, 3 by 4, and that is equals to Z square. And over here on the right hand side, 16, 4 4s are 4 minus 1, 3 by 16. Let's cancel 3 with 3. 16 by 4, that's equal to Z square, and Z will be equals to 2. Atomic number is 2. So option D. I hope this is clear. Let's move to our 6th question. Let's see the 6th one. Okay, great. Pick out the incorrect statement out of the following. Beta emission from the nucleus is always accompanied with a neutrino. Yes. Okay. So it is a beta negative or beta positive? It's beta negative. So beta negative, let me recall, there are 2 types of beta decays. Okay. Pay attention. One is beta positive and one is beta negative. Okay. What do you mean by beta decay? Inside some nuclei, some particular nuclei. Now which type of nuclei? That I won't tell you right now. That is there in higher classes. Okay. Why beta decay happens? Again in higher classes. Okay. In nuclear physics. Okay. So beta decay basically happens inside a particular nuclei in which neutrons convert into protons and protons convert into neutrons to go towards the stability. In a simple sense, they want to get stable. Okay. So to achieve stability, they will convert into neutrons into protons and protons into neutrons. In negative beta decay, always remember electrons are emitted. Electrons are emitted. Electrons are emitted from the nuclei. Okay. And electrons are emitted from the nuclei by simply neutron converts into proton by emission of an electron and an antineutrino. And protons are here converted into neutrons by emission of a positron. What is positron? Antimatter. Okay. So you must have heard these words, antimatter and all stuff in Marvel series movies. Okay. So positrons, okay, plus a neutrino. Okay. So these are the 2 reactions. So even the first statement is wrong because they are saying negative beta decay and a neutrino. No. For negative beta decay, an antineutrino is emitted. Antineutrino. Let's read the other also if there is any other also is wrong. The energy of an alpha particle emitted from a given nucleus is always constant. Okay. Gamma ray emission makes the nucleus more stable. Yeah, all these emissions make them stable. Nuclear force is charge independent. That's also. All other are true. Only A is incorrect. Okay. Let's move to the 7th question. So the 7th question is over here. Which among the following shows particle nature of light? Okay, now this is for all of you. Very common question, million times asked question. Which of the following shows the particle nature of light? Please remember, wave nature of light. Wave nature is given by reflection. Okay, reflection you can prove using wave nature, right? Reflection. You can also prove it using refraction. Okay, wave nature, refraction. Okay, and Newton also tried to prove this reflection and refraction using his corpuscular theory, which was particle nature, but later he was unable to explain the phenomena as like interference. You can't prove interference using particle nature. Diffraction you can't prove using particle nature. Okay, diffraction. And even polarization. Okay, that was omitted this year, but you should know that polarization is also can't be proven using particle nature. Now, in which experiments light behave as particle? Okay, it behaves as particle in a case of photoelectric effect. That was the remarkable experiment in 1900. Okay, it was photoelectric effect, and that led to our quantum mechanics new study. Okay, new branch of physics, that is quantum mechanics. Okay, that is also covered in modern physics. Okay, even the second, they sometimes ask you, okay, just they don't ask the depth of this effect, but actually this is there in the first topic of highest standard quantum mechanics. Okay, starts from here, Compton effect. Okay, now Compton effect also, in this an X-ray is used. Okay, X-ray is light wave, so that also shows a particle nature. So all other things, okay, before 1900 we observed that it shows light as a wave. Light is an electromagnetic wave. It is an electromagnetic wave. Now we know that it is both a wave as well as particle. Clear? So particle nature is shown by these two experiments and wave nature is shown by this experiment. Let's move to our next question, that is question number 8. So question number 8 on the screen over here. It says the mean lives of a radioactive substance are 1620 years and 405 years of alpha emission and beta emission respectively. Okay. The time during which 3/4 of a sample will decay if it is decaying by both alpha and beta emission simultaneously. Okay. Let me explain you in a simple language. There is a nuclei sample. There are some apples which are undergoing decay in some particular interval. Okay. Then there are two types of apple. Okay. So one of them are going in one particular type of decay in this much years, and another beta emission. Okay, of the same sample is going in 405 years. Okay. Now we have to figure out the time in which the number of nuclei or number of apples are becoming 3/4 of its original value. Clear? So let's start writing this. Okay. First of all, okay, you have to know that the decay constant lambda, it is related to half-life as well as it is related to mean life. Okay. So mean means average lifetime. Okay. Sir, when do we find average? Okay, like if you have a nuclei sample which is undergoing different types of decay, alpha, then it went into beta decay, then it is going again into alpha decay. Okay, like that, different types of decay. Then you find a mean time in which how much number of nuclei are undergoing decay. That's your mean. Mean means average. Okay, what's the difference between half-life and mean life? Mean is the average lifetime, and half-life means that time when the number of nuclei becomes half of its original value. That's the major difference between both. Okay. So half-life I have already given you that our T half was equals to how much? It was 0.693 divided by lambda, where lambda was the decay constant, right, or disintegration constant. That was the formula, which we don't require it here now. But here, okay, we have the relation between decay constant and mean life. So tau, okay, that is equals to inverse of your lambda, disintegration constant, straight away. Okay. So can we find the half-life, disintegration constant for alpha particle? That will be 1 upon the tau. Time is how much? How much is the tau here? 1620 years. Okay. So this will be what? Disintegration constant for alpha decay. And what is the disintegration constant for beta decay? It will be 1 upon 405 per year. Correct? So these will be your decay constant or disintegration constant. Don't get confused with these two words. Okay. Some teachers call it as decay constant. Some teachers call it as disintegration constant. Same thing. Lambda is same thing. So what will be the total decay constant or total disintegration constant? It will be lambda alpha plus lambda beta. This is the total. So that will be equals to 1 upon 1620 plus 1 upon 405. Correct? Okay. So this will be your disintegration constant. Okay. This is your equation number 3. Let's simplify it first. Okay. Let's simplify it first. So 1 upon 1620 and 405. Okay. Let's cross multiply and check. 1620. Okay. Plus 405. That will be equals to 2025 whole divided by 1620 into 405. That's 656100. Let me divide this with 2025. That's 324. So this cancels with this, and 1 by 324. That's your lambda. This is from the calculator I did. Okay. This is our decay constant we got for the total emission. Okay. For both alpha and beta decays. Now the next relation I have used at least 2-3 times, okay, in this particular topic, modern physics, and that is a law of radioactive decay. It says the number of nuclei undergoing decay process will always be equal to n naught e to the power minus lambda t. This is the very famous law of radioactive decay. Correct? Now n is what? 3/4 of its original value. So this will be 3/4 of our original value is going decayed. Correct? N is, let me read the question, the time during which the 3/4 of a sample will decay. So what is the number of, okay, 3/4 is decaying. So what are the number of nuclei which are remaining? That will be 1/4. 1/4 is remaining. And if 1/4 is remaining at that time, okay, at that time we have to figure out the value of t. Correct? So let's put here n will be n naught by 4, that is equals to n naught e to the power minus lambda t. Correct? Let me increase the screen size. N naught by 4, 1/4 of the original. Okay, that is equals to n naught e to power minus lambda t. N naught we can cancel both the sides, and we left with 1 by 4 is equals to e to the power minus lambda t. Let's make this e to the power minus lambda t as plus by cross multiplying. So e to power lambda t is equals to plus 4. Okay, or you can take reciprocal both the sides, it's your choice. Okay. Now if we take log both the sides, taking log both the sides, lambda t is equals to log of 4. Correct? Log and exponential will cancel out. Correct? Okay. So lambda t will be equals to log of 4. And what is t will be equals to? It will be 1 by lambda log of 4. I hope this is clear. Now, what is 1 by lambda? So, lambda is 1 by 324 from equation 4 on the screen. So, what is 1 by lambda? 324. So, this implies t will be equals to 324. Let me repeat again. Lambda is 1 by 324. So, 1 by lambda is 324 into log of 4. And what is log of 4? Now, sir, we don't know what is log of 4. So, we can write it as log of 2 square. Log 2 we know. Yes, it's 0.693, right? 0.693. So let's take this 2 in the front. It will be 324 into 2 into log of 2, which is 0.693. Now let me use the calculator and check any option we are getting or not. So 324 into 2 into 0.693, that gives us 449 point some 0. Okay, so 449 is then years. Let me write. So when it will be 3/4, 449 years. Yes, option B is the correct answer for this problem. Let's move to question number 9. So our question number 9 is over here. Okay, again a question from dual nature, which means it will be quite easy. So it says the ratio of the de Broglie wavelength of a proton and alpha particle which have been accelerated through the same potential difference. Very common question. Now instead of this alpha particle, they can also give you electron, they can give you a deuteron, anything, alpha particle, deuteron, proton, okay. Same question repeated a million times, okay. So the question says the ratio of de Broglie wavelength, okay, of a proton and alpha particle. Sometimes it give you proton and deuteron, sometimes they give you deuteron and alpha particle. You should know those properties which I have given you in the chapter that time, moving charges and magnetism we did, okay. So what's a mass and charge of a proton, deuteron and alpha particle? That will help you to solve such problems, okay. Okay, first of all, what's our de Broglie wavelength? Our de Broglie wavelength is lambda is equal to h by p. What's p? P is our momentum, okay. So momentum they are not having here, right? So first we will convert it into kinetic energy. So what will be your kinetic energy formula? It will be root under 2 times m kinetic energy. Now from first chapter, by law of conservation of energy, kinetic energy must be equals to what? Potential energy, we know that. So what's kinetic potential energy? Charge into potential. Sir, from where you got this formula? Second chapter, class 12. Charge into potential is your potential energy. So lambda will be also modified into h by root under 2m qv. 2m qv. Now these all three formulas, the green one, the black one and the blue one, all three are very commonly used formulas. Million times they use it in exams, okay. So here we have to use green one. Why? Because all other are constant, only the potential they are talking about. So ratio of the de Broglie wavelength for a proton and alpha particle, okay. So proton will be lambda proton I am writing, and alpha particle lambda alpha. If they are accelerated through same v, so potential is same. So here it will be h. H is Planck's constant, right? So it will not change even if it is a proton, deuteron or alpha particle or electron. Root under mass of proton mp I am writing, and charge of proton qp I am writing, and potential still remains v. Question 1. This is your lambda p. What will be your lambda alpha? That will be your h root under 2 times mass of alpha particle, charge of alpha particle, and potential remains still v. Correct? Let's divide both. When you divide both, it will become lambda p upon lambda alpha. H will cancel with h. Let's see what are cancelling and which is going on the top. This will become the numerator, right? And this will become the denominator. So when you write the numerator, your 2 will cancel with 2 and v will cancel with v. So you left with root under m alpha and q alpha whole divided by mp and qp. Let me repeat. When you divide the first and the second, the denominator of second will become the numerator. Clear? Okay. Now mass of alpha particle. By now you should know this. If you don't know, then that's a big issue. Okay. So mass of alpha particle is 4 times the mass of proton. 4 times mass of proton. In charge of alpha particle, 2 times charge of proton. These things they will not give you in exams. Mostly in any competitive exams. This cancels, this cancels. 4 2s are 8. 2 root 2. So the ratio will be 2 root 2. Is there any such option? Option C. That's your question number 9. I hope this is clear to all of you. So our last question is over here. An alpha nuclei of energy half mv square bombards a heavy nuclear target of a charge Ze. Then the distance of closest approach of the alpha nuclei will be proportional to which one of them? Okay. See here, this is a question from Rutherford scattering. Remember Rutherford model of atom, where you take, you have done this from 9th standard. Alpha particles are bombarded on gold foil and all, right? So indirect way question of the same thing. Okay. If any charged particle will go, okay, see, pay attention on this. This is the core concept of these type of problems. If you have a charged particle and it is going like this heading with very high energy, it will stop here only if this thing has the energy equal and opposite to this energy, right? There will be some repulsion. There will be some repulsion, and that repulsion only occurs till their energy matches with each other. So who is running here? So kinetic energy of which one? Alpha particle. So alpha particle, alpha nuclei has a kinetic energy half mv square. This energy, when it is equated by the energy of the target. What is the target? Let's see. So heavy target of charge Ze. So if charge is Ze, then what will be the potential energy of this target? Potential energy will be 1 by 4 pi epsilon naught Q1. Q1 is charge of alpha particle into charge on this heavy nuclei whole divided by separation T. So from where you got this formula? Second chapter, U equals to K Q1 Q2 by R, where Q1 is the charge on the first particle, Q2 is the charge on the second particle, and R or D is the separation. So this charge on alpha particle is nothing but the 2 times the charge of proton into Ze upon 4 pi epsilon naught, and I am taking this D on the left hand side, that is the closest approach, and 2 is going here and mv square here. So this will be 4 times Ze square whole divided by 4 pi epsilon naught mv square. So mv square, that is your distance d. Okay, or I have done any mistake? No, this is fine. So this will be your half mv square. Yeah, correct it is. So the distance of closest approach will be proportional to it will be inversely proportional. I think there is a small mistake here. It will be inversely proportional to v square. Okay, proportional to 1 by v square it should be. Okay, there is a small typing mistake. So it should be proportional to 1 by v square and inversely proportional to v square. Be very careful with these words. Okay.